Hello everyone, this is Amit Brambhat, a professor for CSC 208 Discrete Structures. Today we are going to talk about Introduction to Number Theory. Go ahead and share my screen. So welcome to the CS 208 Number Theory. Today we are diving deep into mathematical foundational pillars that quite literally run our modern digital world. While number theory was historically viewed as purest, most theoretical branch of pure mathematics, often called Queen of Mathematics by Carl Friedrich Gauss, computer science has completely transformed it into an intensely practical discipline. Over the next hour or so, we'll move from the absolute basics of arithmetic to the incredibly complex systems that secure global financial networks. We'll explore divisibility, the mechanics of prime numbers, modular systems, and eventually see how these raw algebraic concepts construct modern cryptography. By the end of the masterclass, you won't just see numbers as counting tools, you'll see them as fundamental architecture of cybersecurity and computational logic. So let's get started. Divisibility. Let's begin with a core building block, the concept of divisibility. In discrete mathematics, we say an integer a divides an integer b, written with a vertical bar as a divides b, if there exists some third integer c that b equals a times c. Notice the crucial constraint here, a cannot be 0 and c must be a whole integer, meaning there is absolutely no remainder left behind. If a divides b, then a is a factor of or divisor of b, and b is a multiple of a. On the flip side, if no such integer exists, we write it with a slashed bar. This simple binary property of divides or does not divide, forms the entire bedrock of modular arithmetic. Every algorithm we discuss today relies on checking, tracking, and leveraging these exact integer relationships, making it vital to master this notation immediately. Here are three of the divisibility theorems that you need to understand. Let's move on to the prime numbers. Now we arrive at the atoms of the number line, prime numbers. An integer p greater than 1 is called a prime if its only positive factors are 1 and p itself. If a positive integer greater than 1 has more than 2 factors, it's classified as a composite number. Think of primes as the indivisible elements of arithmetic. They cannot be broken down any further. This brings us to the fundamental theorem of arithmetic, which states that every single positive integer greater than 1 can be written as uniquely as prime number or as the unique product of prime numbers up to the order of the prime factors. This means prime are the universal building blocks, the DNA of all integers. In cryptography, finding, manipulating, and multiplying massive prime numbers is the central mechanism used to encrypt your personal data. And here's a fundamental theorem for prime numbers. Every positive integer greater than 1 can be written uniquely as product of prime numbers, where the prime factors are written in order of non-decreasing size. The division algorithm. It has a traditional name, Division algorithm is actually a fundamental mathematical theorem, not a step-by-step computational procedure. It states that for any integer a and positive integer d, there exists unique integers q and r such that a equals d times q plus r. Here, q represents the quotients and r represents the remainder. There is a strict unyielding constraint on the remainder. It must be greater than or equal to 0 and strictly less than the divisor d. This uniqueness property is beautiful because it guarantees no matter how large a number is, when you divide it by a fixed base, there is only one possible quotient and one possible remainder. In computer science, we extract these two components daily using the integer division operator and modulo operator. GCD or greatest common divisors. When working with pairs of integers, we frequently need to find their greatest common divisor or GCD. GCD of two non-zero integers a and b is the largest positive integers that divides both a and b simultaneously without remainder. For example, the common divisor of 24 and 36 are 1, 2, 3, 4, 6, and 12, making 12 their GCD. On the right side of the slide, you'll see a crucial definition. When the GCD of two numbers is exactly 1, we call those numbers relatively prime or co-prime. This means they share absolutely no common prime factors whatsoever. Co-primality is incredibly powerful property in computational algorithms, particularly when we need to guarantee that mathematical inverse exists within a modular system. Relatively prime integers. Two integers a and b are relatively prime or co-prime if their greatest common divisor is 1. So GCD of a and b is 1. That means it's relatively prime. And there are examples for the same where 15 and 28 are relatively prime. So are 55 and 28, but 35 and 28 are not relatively prime because their greatest common divisor is 7. Least common multiples. The least common multiple of a positive integer a and b is the smallest positive integer that is divisible by both a and b. So LCM is the notation for least common multiples, LCM of a and b. And the examples here given are LCM of 3 and 7. Since 3 and 7 are prime, LCM of 3 and 7 is 21. LCM of 4 and 6, the first match is 12. And LCM of 5 and 10 is the 10. The GCD and LCM relationship. For any two positive integers a and b, their product is equal to the product of their greatest common divisor and least common multiple. A dot b is GCD of a and b multiplied by LCM of a and b. And here we also have a worked example. I suggest that whenever you're working through examples, you pause your video and understand the slide thoroughly. Modular arithmetic. So let the modulo operators are simply denoted by a mod m, where a is an integer and m is a positive integer. Examples are 9 mod 4 is 1, 9 mod 3 is 0, 9 mod 10 is 9, and minus 13 mod 4 is 3. And you're given how it's calculated. Congruence modulo m. Congruents are not just static definition. They form an entirely operational algebraic system. They behave beautifully under standard arithmetic operations, almost exactly like traditional algebraic equations. As theorems on the side demonstrate, if A is congruent to B and C is congruent to D under the same modulo M, we can freely add or multiply these expressions together. Specifically, A plus C will remain congruent to B plus D, and A times C will remain congruent to B times D. This means that when you're performing complex massive computations, you can reduce your numbers modulo m before performing additional or multiplications, rather than waiting until the end. This prevents computational arithmetic overflow and keeps our data sizes highly optimized for CPU processing. So congruence is equivalent to saying you can look at the theorem and equivalence here, that A and then 3 lines is the symbol for congruence. B in brackets mod M means A mod M equals B mod M. And there is an example, worked example of 17 congruent with 5 mod 6, where the final answer comes out to be 12. The Euclidean algorithm. While finding GCD of small numbers is easy, doing so for numbers that are hundreds of digits long requires a highly efficient computational approach. So that's why we need to learn Euclidean algorithm. One of the oldest and most elegant algorithms still actively used today is Euclidean algorithm. Its core mechanics is incredibly clever. The GCD of two numbers does not change if the larger number is replaced by its remainder when divided by a smaller number. As outlined in the workflow on the slide, we continuously compute remainders in a loop. We take A mod B, update our variables, and repeat. The moment the remainder hits exactly 0, the algorithm terminates, and the very last non-zero remainder is mathematically guaranteed to be greatest common divisor. It bypasses the need for costly prime factorization entirely. Representation of integers. So here we are given examples of positional number bases and common computing bases. So we see that decimal is the base 10, the standard human counting system. Binary is base 2, which uses bits 0 and 1, and it is perfect for logic gates. Hexadecimal has base 16, uses digits 0 to 9 and capital A to capital F. It is a compact memory representation. Binary addition and carry. So bridging the gap between the pure number theory and physical hardware engineering, we need to understand this concept. Computer processors don't think in base 10. They utilize binary logic circuits operating entirely in base 2, which is mathematically equivalent to working modulo 2. Look at the truth matrix on the slide, which tracks basic binary addition. When we add 0 and 0, we get 0. When we add 0 and 1, or 1 and 0, we get 1. When we add 1 and 1, we result in 2, base 2, which is 1, 0, meaning the sum bit is 0 and 1 is carried over for the next column. In the computer logic hardware, this exact addition operation is executed using exclusive or XOR gate for the sum and the AND gate for the carry bit. Hardware arithmetic is fundamentally modular arithmetic at its fastest scale. So moving on to cryptography, how the number theory enables computer security and mathematical secrecy. This is where the number theory transitions from an elegant mathematical study into a vital shield protecting global infrastructure. Cryptography is the art and science of hiding information, transforming readable plain text into unreadable ciphertext to prevent unauthorized access. Historically, ciphers were simple linguistic tricks or mechanical puzzles. However, in the internet age, cryptography is purely algorithmic and mathematical. The security of your bank transactions, private text messages, and cloud storage data relies entirely on the mathematical difficulty of solving specific number and theoretical problems. We'll trace this evolution from primitive ancient techniques to the sophisticated asymmetric systems that secure our modern digital world. To understand cryptography, we must establish its standard, universal terminology. We begin with plain text, which is the original unencrypted message in its readable format. This plain text is passed through encryption algorithm fueled by specific encryption key, converting it into a ciphertext, which is completely scrambled, unreadable data. To read the algorithm using decryption key to recover the original plain text is illustrated in the workflow diagram. Uh, the goal is to make computationally impossible for an adversary intercepting ciphertext to reverse engineer the plain text without possessing the correct mathematical key. The math itself acts as a secure lock. Here, I recommend that you read through the cryptography PDF provided in your course material and understand the concepts that are provided within that PDF. Classical ciphers, Caesar and substitution. Let's look at where it all began. Classical cryptography. The most famous early systems in Caesar cipher used by Julius Caesar. It's simple monalphabetic substitution cipher where each letter in plain text is shifted down the alphabet by a fixed number of positions. Mathematically, we can map letters to numbers 0 through 25, turning encryption into a clean modular equation. F of P is P plus K mod 26, where K is our key shift. While revolutionary for its ancient time, classical substitution ciphers offer virtually zero security today because they preserve the underlying structure of the language. They can be cracked in seconds using frequency analysis, counting which characters appear the most often to easily deduce the key shift. Mechanical cryptography, the enigma. As history progressed, cryptography moved from simple handwritten tables and into the realm of complex mechanical engineering. The most prominent historical example is the German Enigma machine, heavily utilized during World War II. The Enigma was an electromechanical rotor machine that scrambled the alphabet. Every single time an operator pressed a letter key, the internal mechanical rotors would physically turn, changing the electrical circuit and ensuring the exact same letter would encrypt differently each time it was typed. This eliminated traditional frequency analysis. Breaking the enigma required a monumental blend of linguistic insight, stolen codebooks, and early electromechanical computing machines designed by Alan Turing and his team at Bletchley Park, a historic breakthrough that laid the direct groundwork for modern computing science. One-time pad or OTP. In the realm of secure communication, the one-time pad or OTP stands alone as the only mathematical unbreakable cipher. It achieves what cryptographers call perfect secrecy. The concept is straightforward. The key must be a completely random sequence of characters that is at least as long as the plain text message itself. It can only be used once and it must be kept entirely secret. To encrypt, we combine the plain text and the key using bitwise modular addition, specifically XOR operation. Because the key is entirely random, the resulting ciphertext is also completely perfectly random. An adversary with infinite computing power could try to brute force it, but they would only generate every possible readable text string of that length, with absolutely no mathematical way to determine which one is the real message. I suggest that you pause the slide and understand perfect secrecy and key reuse disaster from this slide. Symmetric versus asymmetric cryptography. Modern cryptography is broadly split into two main paradigms, symmetric and asymmetric. Symmetric cryptography uses exact same shared secret key for both encryption and decryption. It's incredibly fast and highly effective for encrypting massive amounts of data, but it suffers from massive logistical flaw. How do two parties securely share that initial secret key over an insecure internet without someone intercepting it? To solve this, we use asymmetric cryptography, also known as public key cryptography. Here, every user has a mathematically linked key pair, a public key, which is distributed openly to entire world for encryption, and a private key, which is kept secret for decryption. This completely eliminates the dangerous key exchange bottleneck. Diffie-Hellman key exchange. The breakthrough solution to the key exchange problem came in 1976 with the Diffie-Hellman key exchange protocol. It allows two parties, traditionally named Alice and Bob, to establish a shared secret key over an insecure channel without exchanging the key itself. The protocol relies on mathematical difficulty of computing discrete algorithms in a finite field. Logarithms in a finite field. Alice and Bob agree on a public prime P and generator G. Alice chooses a secret integer A and sends Bob G of A mod P. Bob chooses secret integer B and sends Alice G of B mod P. They each raise the received value to their own secret exponent. Due to the commutative property of exponents, they both arrive at the same exact shared key, while eavesdropper is left with an intractable math problem. The RSA cryptosystem. The most widely deployed public key cryptosystem in history of is RSA, named after its creators Rivest, Shamir, and Edelman. Its security relies on a beautifully simple asymmetric property of number theory. Multiplying two massive prime numbers together is computationally easy for a computer, but factoring that massive product back into its original primes is incredibly difficult and time-consuming. To set up RSA, we choose two massive primes, P and Q, and compute their product n. We calculate Euler's totient fraction function n, pick an encryption exponent E that is co-prime to that totient, and calculate its modular inverse D to serve as the private decryption key. The public key is open to anyone, but decryption requires the private factor key, locking the data safely and behind prime numerical complexity. As crypto systems scale, processing speed becomes operational bottleneck. To optimize the performance, modern implementations utilize advanced number theory concepts such as Chinese remainder theorem or CRT. CRT is a powerful ancient theorem stating that single integer can be uniquely identified by its remainders when divided by a set of pairwise co-prime moduli. In RSA decryption, instead of performing massive sluggish modular exponentiations modulo a gigantic number n, the CRT allows us to split that single massive calculation into much smaller lightning-fast computations, one modulo p and the one modulo q. By processing these parallel streams separately and combining the results at the end, we achieve a massive 4 times acceleration in decryption speed. Here are a couple of worked examples where basically we are trying to find x in the range such that range is 0 to 54 and x CRT'd with 4 mod 5 and x with 7 mod 11 are the examples we are solving for. The numbers congruent to 7 mod 11 are 7, 18, 29 and 40, and which brings us to x being 29, solving which satisfies both the conditions that are given earlier in that practical example. If you have any questions, feel free to reach out to me via email or send me a message through Canvas, and I'll be sure to respond to your queries. I hope you enjoyed the class and learned quite a bit about number theory and its usage in cryptography. Take care now. Bye.